Hey there, everybody. It is time to get your muscles pumped up. Get your weights, get your yoga mats, get your walls to do some wall sits, whatever it is you want to use to work out. And let's take a little bit closer look at muscle contraction. So we are going to talk about a few terms first: isometric, isotonic, and eccentric contractions. Okay, so first let's talk a little bit about working out. Hopefully you have been exercising, you've been keeping your bodies working and your blood flowing to make your brains think. Remember, we need glucose and oxygen into our brains to make lots of ATP to think about all this stuff. All right, now, if we talk about different types of muscle contraction, the first one we can talk about is isometric contraction. Now, if you see over here, here is some example isometric moves that maybe you're into, some push-up holds, there are the hip thrust hold, you could do planks, you could do wall sits, squats, right? All kinds of different ways to do these isometric workouts. But basically what we're doing with isometrics is we are creating some kind of internal tension while we're creating an external resistance. Okay, so we're creating internal tension on that muscle. So that muscle is staying the same length, and we're not moving those joints. So we're creating a lot of force and tension on that muscle. Okay. Now, if we look at isotonic contraction, isotonic contraction can then be divided into two types of contraction. So the first is concentric contraction. And so basically, you can see both of these two individuals are doing some bicep curls here. And so what we're doing with concentric contraction is shortening our muscle and maintaining tension. So as we're slowly moving this up, we're creating tension on those muscles, and that muscle is getting shorter. We're moving that insertion towards that origin. And this is going to encourage hypertrophy of that muscle. It is effective in producing muscle mass, but it's much more beneficial when you are working concentric exercises with eccentric exercises together. And so what is an eccentric contraction? Well, this is going in the other direction, so moving that weight down and lowering it down slowly. So as we have that tension maintained in that muscle, we are then lengthening that muscle. And so again, using these two exercises together is really beneficial. When you think about just bringing something up and then you just kind of let it fall down, maybe you've seen some people do that in the workout room where they're jamming that thing up and then just let it flail down. And so that can be pretty tough on those joints and those muscles, and you can cause some injury doing that. So it's really good idea to slowly let that come down and build that tension in those muscles. Now, if we talk about the forces of contraction, we have a few things to look at here. Okay, and first off, we can see that we've got our graph here. So on the side, we've got tension. And then on the bottom, we've got our time and our milliseconds, okay? Now, we've got three different periods along here. So we've got our latency period, we have our contraction period, or contraction phase, and then we have our relaxation phase, okay? And the relaxation phase is fairly big. So a muscle twitch, when we talk about a muscle twitch, it's the response of the muscle to a single brief threshold stimulus. Okay, so a single brief threshold stimulus, meaning that muscle hits threshold and fires. It is basically the simplest form of contraction when we're in a lab, okay, experimenting with this. Now, in that latency period, you'll notice it's offset a little bit. It does not start right at 0, okay? And so it's about a 2 millisecond delay that happens from the onset of a stimulus and that twitch response. So if you remember those steps from our last lecture, excitation coupling, and basically adding tension to those elastic components, so that if you're thinking about pulling a car with a rope or pulling a car with a rubber band, right, there's a little bit of elasticity on there, and so we have to kind of remove that elasticity to get some force. And so in that time for that excitation to happen and that excitation coupling to happen and then removing that tension, that takes about 2 milliseconds. Then we get into our contraction phase, okay? And so this contraction phase is when those muscle filaments are sliding past each other, okay? So once those elastic components are taut, then that muscle starts to produce some external tension, okay? And that's going to help move that load that we're trying to act against, okay? And then last is our relaxation phase. And so this is when our sarcoplasmic reticulum is reabsorbing that calcium. The myosin heads are the cross bridges are breaking. Our troponin, tropomyosin complexes are covering up those active sites. So basically, our muscle is returning to that original resting length, and so that entire twitch can kind of be anywhere between 7 and 100 milliseconds here, 140 milliseconds. Now, what's kind of cool is that humans take about 180 to 200 milliseconds to detect and respond to some kind of visual stimulus. So if that gives you any idea as to like how fast you go, so maybe take a stopwatch and see how fast you can turn it on and turn it off, and then kind of think about your responses here with your muscles. So it's pretty quick. Now, when we talk about our contractile forces, we have a few different characteristics or a few different qualifiers here, right? And so the strength of that contraction is going to be governed by one, our number of muscle fibers that are activated. Okay, so if we have more muscle fibers activated, we're going to have more force. If we have larger muscle fibers, then and they're thicker, then they're going to generate more power because we're going to have more myofibrils in that space, and therefore more thin and thick filaments that can then move those sarcomeres closer together. We can increase the frequency of our stimulation, and that's going to give us more force, and our initial length of those muscle fibers when we're at rest. So we're going to look at each of these four and go into a little more depth. Now, the first one, the number of fibers that are being stimulated. We talked about this in the last lecture, and if you remember, we said we have one motor neuron that's going to innervate onto, in this example, 4 muscle fibers, another motor neuron that's innervating into 4 muscle fibers. If both of those motor neurons are fired, then we have 8 muscle fibers that are stimulated. And so we said with real fine dexterity, we had maybe 3 or 4 or 5 muscle fibers, but if we have real big movements generated, then we need hundreds to thousands of these muscle fibers. And so that's really important when you think about picking up a pen, right? We don't need to generate all of this force to pick this thing up, right? We get this visual information that's coming in. We know we have this conscious thought of, I need a pen. I look at the pen and I have this learned response that I know about what a pen weighs. And so when I'm going to pick that up, I know that I don't need to fire all of these hundreds of muscle units in order to make this happen, right? When you're writing, it's much more gentle, much more fine-tuning of those muscles. maybe you've experienced this when you go to pick up a box and you think it's much heavier than it actually is, and there's like nothing in it, and you're like, whoa! You're like, holy cow, that's hilarious, because you thought it was going to be a lot heavier and it wasn't, and so you've initiated all of these motor units to help you pick it up, right? Or the opposite is true. You think it's going to be really light and it's actually really heavy, and so you go to pick it up and you're like, oh, I can't move that, and so then you have to kind of give it a second shot. Now, number 2, with our fiber size, we talked about these two terms, hyperplasia and hypertrophy, back in Unit 2. So if we talk about hyperplasia, we're increasing the number of fibers. If we talk about hypertrophy, we're increasing the volume or the size of those fibers. And so to get all beefed up like this dude, we are, kind of shooting for this myofibrillar hypertrophy, because this is going to increase that the number of myofibrils and myofilaments that are in there, and that's going to generate more force. Now you'll see up here sarcoplasmic hypertrophy. Sarcoplasmic hypertrophy is sort of increasing the amount of that sarcoplasm, or that cytoplasm that's in there, right? And so we tend to see this with like creatine supplements, where we're taking on water in those muscle cells, and so they get bigger, but they don't actually necessarily generate any more force. So when we're working out, doing those isometric or isotonic workouts, we're wanting to generate more of this myofibrillar hypertrophy. Okay, now this is 3 little images that are over here that all sort of interrelate, and so we're going to walk through these first, and this is all in relation to stimulation. Now, when we talk about our threshold stimulus, so our threshold is about negative 50 millivolts here on these muscle fibers. And so again, just like we saw with neurons, we had to get to threshold before we can have that signal pass down, before we can generate action potentials. So that threshold stimulus is our first observable muscle contraction, which we can kind of see just hidden behind that box right there. When we look at the proportion of motor units excited, we can see we have none here, and we have many, or all, I should say, down here to the right. So as we increase our stimulus strength, we're going to increase muscle contraction, because we're recruiting more motor units, which we talked about earlier. And then as more of those motor units are recruited, we generate more contraction. Okay, so if we look at this all together, here we are with basically no motor units recruited, so no stimulation, or very little stimulation, and that little stimulation isn't enough to get us to our threshold. So we're not going to have any firing of our motor units, and therefore we're going to have no tension. That should make sense. But as we increase our stimulus and we reach threshold, well, now we can see we've stimulated a couple of motor units and a little bit of muscle tension, so maybe picking up something a little bit smaller. As we increase the stimuli, we increase more response, and we have more motor units as we go across this diagram. So we're increasing here to 4 motor units, and again you can see down here we have more tension, and that tension is increasing. So here at 5 stimuli, then we have more motor units recruited, and we have more tension, and as we move across we are doing the same. Now at some point, when we recruit all of those motor units, even if we increase the number of stimuli, we've recruited all of those motor units that we possibly can, and so we get to a maxed out contraction. Okay, we cannot move anymore. We have no more ability to generate tension. All right. Now, sort of falling under we're going to look a little bit more into stimulation. So what does that look like? All right, now when we talk about these muscle twitches, you can see here we've got our stimuli coming in. And if we are talking from 0 to about 10 stimuli in a second, we get these individual twitches, and then we have a full recovery of that muscle fiber, right? So that full relaxation, full recovery back to normal. And then we have another stimulation and full recovery, and another stimulation and full recovery, right? And so we're getting a little bit of those muscles twitching. Now, if we look at maybe about 10 to 20 stimuli per second, we call this trepa, or like a staircasing, okay? And so what's happening is we get a stimulation and we get full recovery between those twitches, which is developing a little bit more tension on that muscle. But what you notice is that that sarcoplasmic reticulum doesn't have time to reabsorb all of that calcium, okay? And so there's residual calcium in that cytosol, and when we get another stimulation, we have all of that process going on that we've talked about previously, and we get a little bit more force here, or more tension. And so that calcium concentration increases as we have more twitches, more stimulations, and those are going to open as that calcium increases in concentration. That's the key. That's gonna open up more of those troponin, tropomyosin complexes, and open up more binding sites and allow for more binding of those myosin heads. Now, as this continues, we get more tension in that muscle. And the heat that's released by these twitches then is going to increase our efficiency of our muscle enzymes, so that ATPase, and we're going to eventually have stronger twitches as our muscle is warming up. So when your coaches and trainers are telling you to warm up, it's because it's increasing your enzyme efficiency and your muscle efficiency. So this is really important to allow this to happen for 10 to 15 minutes, 30 minutes before your activity, because then when you come into that activity, you're ready to go, you're going to be a lot stronger and a lot more prepared. Now, there's a term used called tetanus, and so this is sort of our maximum contraction with our muscles. We're sort of in this steady state. Okay. Now, when we're in a tetanic state, the muscles can shorten and lengthen, but they're at their maximum tension. Okay. Now, there's two types that we can look at: incomplete tetanus. Now, when we look at about 20 to 40 stimuli per second, what we're seeing is that we're getting in new stimuli coming in before the previous twitch is over. And so it's sort of piggybacking on the previous twitch, generating more tension in that muscle. So there is a little bit of this recovery, but not full recovery. And so when we call that temporal summation, where we're getting those stimuli right over time, two stimuli coming in real close together. So that muscle is sort of relaxing only partially between those different stimuli. And that's going to create sort of this sustained fluttering contraction, which is called incomplete tetanus. On the other hand, complete tetanus, then, if we increase our stimuli even more, there is no time to relax between stimuli. And so this creates this smooth, prolonged contraction that is called complete tetanus. So when we think about that, holding up a box or holding ourselves up in a like a wall sit, we're in a complete tetanus state. All right, now the last characteristic that we wanted to talk about, which is going to generate muscle force, is our sarcomere length. So again, let's look at our graph. Here on the left, we can see tension that is in our muscles. On the bottom, we see the percent of resting sarcomere length. So if we measured the sarcomere at rest, and then we can basically talk about the percentage of it. Or so on the left here of 100 or lower than 100%, it's a little bit shorter. If it's to the right of 100, it's overly stretched. If we are overly contracted, meaning our sarcomeres are shortened, so if you think about picking up something, but if you're in this state already, your sarcomeres are already shortened, and so the force that you can generate in this movement is much less than if your sarcomeres were at rest or in their optimal range. So if you are a little bit shorter, if those sarcomeres are shorter, then the Z discs are too close together, and you don't get that force that you're hoping for. If they're overly stretched, then you can see right in here, right, we don't have as much overlap between the thick and those thin filaments, and so there's not going to be as much binding going on, and it's not going to allow for those cross bridges to be there, so we're going to have, again, less force. And so our optimal operating length is somewhere between 80 and 120% of our resting length. We have enough of these myosin heads that can form cross bridges. And so our central nervous system is constantly monitoring this, and it's kind of adjusting the length of our muscles. So all that sensory information that we're sending back to our brains and back to our integration centers are processing where our muscles are, all those proprioreceptors, right? All those stretch receptors that we were talking about. And so that central nervous system is kind of going to adjust the length, and it's going to maintain our muscle tone, sort of this partial contraction. And if you remember when we talked about the autonomic nervous system, we had vasomotor tone, where our blood vessels were in a partially contracted state, and so if we increased the stimulation, they would constrict more. If we kind of turned it down, we would kind of dilate. And so same sort of thing is going on here, where those muscles are in this sort of partially ready, partially contracted state. And so we're going to maintain that optimum length and really have those muscles ready for action. So that brings us to the end of our third muscle lecture. Please do spend some time going over this information, talking about these 4 characteristics and how they influence muscle contraction. And I will see you on our next lecture for our final lecture of muscles and talk about muscle metabolism. Have a wonderful afternoon.